22,000 metric tons. That is the drilling mode variable deck load the GF 12,000 is actually rated to carry. Welcome to today's explainer, where we're unpacking a really fascinating engineering paradox. So we are looking at this massive vessel, right? It's basically a 6-story building made of steel with 3,600 square meters of deck space. But, the real story here isn't her size. It's how her capacity completely changes depending on what she's actually doing. And this brilliantly illustrates the mystery we're going to solve today. You've got this massive 22,000 metric ton limit while she's drilling, but then it drops down to 17,000 the absolute moment she prepares to move. It's the exact same ship, the exact same deck, the exact same tanks, and yet her approved capacity shrinks significantly just by shifting from drilling mode over to transit mode. That is nearly 5,000 tons of capacity that literally just vanishes, gone, from the exact same ship just because her operating mode changed. To put that into perspective, that is the equivalent weight of roughly 25 fully loaded Boeing 747s that are suddenly totally off limits. You definitely can't just leave that weight on board and sail away safely. Section 1. What exactly is variable deck load? Plainly spoken, VDL is everything that isn't the ship itself. It's the payload, and it sets a really hard ceiling on safe operations. Think about it like this. If you strip away the hull, the permanently installed thrusters, the derrick, and the engines, what you have left is the light ship weight. Absolutely everything else you stack on top of the deck or pump inside the tanks, that is your variable deck load. Now, the sheer volume of materials eating up that budget is just staggering. And honestly, it changes constantly as you're out there pumping mud down hole or loading new pipes. A drill ship's entire purpose in life is to carry these massive consumables out to a deep water location and use them all up over the course of a well program. For a real-world example of this, a single 10,000-foot riser string made of 40 to 50-inch pipe can weigh well over 1,000 metric tons in the air. That instantly eats a massive chunk of your capacity. That incredibly heavy pipe has to be racked and stored securely on board, which means it consumes nearly half of your drilling mode budget before you even start to factor in things like fuel or crew stores. Add to that the wild fact that you're carrying more mud than an Olympic swimming pool, and then 3 times that volume in fuel oil. It's crazy. This massive liquid payload just sits right down in the tanks of the double hull, and just like the physical pipe on the deck, it counts directly against your VDL. Moving on to Section 2, why exactly does this limit flex? When planted in drilling mode, she sits deeper in the water at an 11-meter draft, which actually provides more reserve buoyancy. But in transit mode, she rides higher at 9.5 meters to navigate the open seas safely. The crew actually floods the ballast tanks deliberately to sink the ship 1.5 meters deeper when drilling. It acts almost exactly like a submarine, trimming its buoyancy. This lowers the center of gravity relative to the waves and provides a much calmer ride for that rigid riser connected to the seabed. The key insight that most people completely miss here is that VDL isn't some fixed cargo capacity, like a moving truck's payload rating. It flexes because the underlying safety margins flex too. A drill ship has this highly dynamic engineering envelope that is dictated by its draft, its stability margins, and how the hull structure handles the absolutely incredible stresses of the open ocean. Think of VDL kind of like the maximum passenger count on an elevator. That number might change depending on whether it's climbing or just standing still. This is the real revolution here. The vessel is simply allowed to carry more while it's planted deep, taking advantage of the stabilizing benefit of a deployed riser, than while it's actively moving through unpredictable waves. The ship in transit has to contend with heavy weather without that stabilizing connection to the seabed, so safety regulations mandate a lighter load. Makes sense, right? All right, Section 3, calculating your safe departure. The vessel's loading computer and stability software are continuously cross-checking these real-time metrics against class-approved limits to ensure the ship is actually safe to transit. The master of the vessel and the ballast control officer watch these numbers like a hawk. They're constantly verifying that the ship's center of gravity isn't creeping up too high as heavy pipe gets shifted around the deck. Because exceeding the approved VDL, even briefly, raises the vessel's center of gravity and creates a literally lethal capsizing risk. This makes it an absolute hard rule. It is not just a polite guideline. If you are overloaded and you hit severe weather, the vessel's natural ability to right itself after taking a massive wave is severely compromised. It's a silent killer out on the water. So you must use this specific formula to plan your supply boat backloads before any transit can begin. It looks super simple on paper. Available VDL remaining equals your approved VDL limit minus your current deck and tank load. But applying this across thousands of individual items, from massive blowout preventer parts down to literal bags of cement, is a monumental logistical task for the crew. Let's actually test this with a real-world scenario. Say you are finishing up a well, and your current load is sitting at 20,500 metric tons because you just pulled all that heavy pipe out of the hole. But your transit limit is firmly set at 17,000 metric tons. What is your next move? Take a quick second to calculate the required offload. Did you get it? You have to offload at least 3,500 metric tons onto a supply vessel before you can safely get underway. And remember, you absolutely have to build in a margin for planning error, so you can't just aim for exactly 17,000. You definitely need some buffer room there. Cutting it close to the VDL limit on moving day risks massive operational delays, or worse, devastating classification violations. That is exactly why the golden rule on these rigs is to plan your backload operations at least one full supply run before a planned move. You really do not want a multi-million-dollar drillship stuck waiting on a supply boat just to legally drop its weight before it can sail. Which leaves us with a pretty provocative thought about how we perceive the limits of the machines in our everyday lives, which are constantly shifting beneath our feet. We tend to think of structural capacity as a fixed, permanent number, don't we? But out on the deep ocean, engineering boundaries are essentially alive. They adapt to the environment, they adapt to the mission, and they demand absolute respect. It really makes you wonder, what other limits in our engineered world are actually flexing in real time while we blindly trust them?